Hello everyone, we need to continue. And in last week, we focused a lot on the k-nearest neighbor. And even though this is a really basic, really simple machine learning algorithm, and when we dive into that, there are a lot of things we need to discuss. For example, like the distance matrix, like the one-hot encoder, and how we are gonna pre-process the data before we really send the data into the k-nearest neighbor. And in addition, how do we pick the right k-value? So even for a small, very basic machine learning model, there are a lot of things we need to discuss. However, we have to move on to other machine learning algorithms because one machine learning algorithm, KNN, does not solve all the problems. So today we are going to move on to naive Bayes. But before we start, let me give you a scenario that the k-nearest neighbor may not work that well. For example, we want to build a machine learning model and we want to predict how a person is going to vote in the next presidential election. So we want to predict a very specific case. And in that case, we are trying to predict a male Hispanic person, and he has a high income, and he lives in the U.S. Midwest, and he voted in the last election, but he didn't voted in the even prior one. And this person has three daughters, one son, and this person is currently divorced. Okay, so we are very specific, and we want to predict this person. Okay, so even we have a big data set, and it will be very hard for us to find exact matches. Well, if we want to match all those eight criteria, and it will be hard. And you may ask, why do we want to find exact matches? Consider if we are doing the k-nearest neighbor, and if we have a exact match, what is that? That is a close neighbor. It's a possible closest neighbor because the distance between the current sample to the neighbor we find is actually a zero because that is the exact match, right? So this is a bad thing we want to do. So for this person, if we can find five closest neighbor and there are five exact matches or 10 exact matches, that will be the best thing because we can use exact matches to predict how this person is going to vote. However, how about we don't have that? In this case, we don't have any exact matches, and what will happen? So we have to select some of the criterion a little bit. So for example, for race, say we can find an Asian person. This person has all the other attributes exactly the same. However, this person is not Hispanic, he's an Asian. So do you want to consider this person as a close enough neighbor to the sample we want to predict? Or if we have another possible candidate, and this person has all the attributes to be exactly the same except for the number of the sons. So in this case, do we want to pick the Asian who has all the remaining attributes to be the same, or we want to pick another sample has the num of the sons to be different and all the remaining samples to be remaining attributes to be the same? So in this case, how are we going to find or how are we going to define the closest neighbor? And this can be challenging, right? And in addition, well, if you consider for the gender, for the race, well, and for the location, they are categorical features. They are not numerical features. And of course, we have to do a one-hot encoder. And in addition, for the income, this can be considered as a numerical feature, for example, and then we have to do a standard scalar. So even we are only dealing with eight attributes, and you may find it's hard to apply k-nearest neighbor to this kind of case. So we have to switch to another machine learning algorithm in this case. So before we formally introduce you the naive Bayes, I want to use a sieve and a dog bark example. And you guys may know Dr. Mark is a dog person, right? So we are gonna use him as an example. So For the naive Bayes theorem, let's consider this case. So if Dr. Mark is sitting in his couch and all of a sudden he hears that his dog barks. Okay, in this case, is there really a thief there? So does Dr. Mark need to grab his baseball bat immediately in case a thief is coming? So to solve this problem, let's assume some of the values. So let's say, well, he has a relatively noisy dog and the dog barks 10% of the time. And well, Dr. Marks lives in a relative safe community and the probability of having a thief is very low. And well, let's also assume that his dog is protective enough, and when the dog sees a thief, and it will bark, guaranteed. Okay, so we are dealing with this kind of probability. So the probability we are going to discussing will be the probability of the dog bark, and at the same time there is a thief. So this is the probability we are going to discuss. The dog barks and at the same time there is also a thief. So what does this equal to? It equals to the probability of the dog bark and multiply by the probability of a thief is really here given the dog barks. Okay, so this part is the probability of the thief is really there given the dog barks. Okay, so this also equals the probability of a thief and the probability of the dog bark given the thief is really there. Okay, so do you guys see how it works? So we have the probability of the dog bark and at the same time there is really a thief. So this part, this is the joint probability, and it equals the probability of the dog barks multiplied by given the dog barks there's really a thief. So we can read this as given the dog barks and then there is really a thief. And it also equals the probability of a thief and multiplied by the probability of given the thief is there, the dog barks. Okay, so there are a total of 4 variables in this part of the formula. Okay, so if we want to move the p bark from the left side to the right side, and then we will figure out the probability of given the dog barks, what's the probability of there is really a thief. And if you use those 3 values, you can figure out the remaining value, which is given the dog barks, the probability of there is really a thief. And you will see the probability is really low, and this means, well, among 10 millions of the times that Dr. Marks grabs a bat, we expect there's only one thief. So what does this mean? So for Dr. Mark, when he hears his dog barks, he doesn't really need to grab a baseball bat because the probability that there's really a thief there is very, very, very low. Okay, so let's forget about the p bark, p thief, and all those things. Let's just use the px, py, and px given y, py given x, and then we will have this. So the joint probability of the of the x and y happens together will be the py given x multiplied by px, and it also equals px given y and multiplied by py. And in this case, if you know 3 terms and you want to know the remaining one, what you need to do will be simply something like this. And what is that? So that is the Bayes theorem. Okay, so this is introduction of the Bayes theorem, and this is the theoretical part. And I will see you in the next video.